好，开始好了。
这方可以的。
有，现在开始了。好吧。
Okay. Let us begin our class today. First of all, I heard from my assistant that you have some question about the homework. The homework, I believe that the determine frequency response function from Z cap R to ZC. No problem, right? Any problem? No? Okay. Only the second problem for the plot, I don't see any problem for that. The second problem say that you are allowed to change ds. You're allowed to change this ds. Then choose the ds sub s such that the car transient responses without counting the wheel dynamics. The wheel dynamics means that, for example, if I don't have this wheel, this is wheel dynamics including MW, assume that this MW just touched to the ground, it's on the ground, like that. And so that's almost exactly the same example I give to you in the class, in the note. The understanding now? So just assume that we have MC, KS, and DS, and that touched, and then it touched the ground. That's it, no wheel. This car has no wheel. Any problem like that? All right, if there's no questions, then I assume that you don't have any problem. Okay. All right. And then we are talking about transient response. Here I said transient response. It's not steady state. FIF, we talk about steady state. But this is a system itself. All right, it's a transient response. The transient response, you don't talk about the FIF at all. Okay. If there's no more questions, let us go back. You have to switch to response now. Okay, the response. Okay, we need to switch to response. Okay. Somehow we need to provide a tool, software that they can switch automatically. You don't have to do this anymore, right? That's better. Okay, now let us let me move quickly to the page, last page. Well, I think this is only the way to do it, right? Maybe. Okay. Last week, I think we discussed up to the 2 degree of freedom examples, and we talked to this frequency response functions, and then we discussed about the peak, and we discussed about the pole. The pole in control terminologies, it means it means the eigenvalue of the system. All right, that's the pole. That's at the peak here. That's the pole, and that pole, if you look at frequencies, in these frequencies corresponding to 2 frequencies. So there are 2 poles for this system because we have 2 degree freedoms, and then so we have 2 poles. If you have only 1 degree of freedom, you're supposed to have only 1 pole. So even that we have the second order system here, the second order, the denominator here, and so we have, in matter of fact, we have a Paul here, we have Paul there. Although we have two roots here, but they are complex conjugate. So when you have a complex conjugate, you take absolute value. The absolute value is the same thing. Right? Agree? So that's what we have a two Paul here. And if you look at G11 and G12, both transfer functions, we know that G11 is from the first input to the first output. G12 is from second input to the first output. All right? And it doesn't matter what, they share the same Pauls because they do have the same denominator for their transfer functions. They have to be like that. So in your homework, it will be the same thing. All right? So that we have here now, we do have the two Paul here. However, if you look carefully, this blue line, we have a sharp, I call it valley, right? It is like a mountain. Valley here is a sharp valley, and that we call zeros. And that's only occur in the same location of input and output. So from first input to first output means the input and output are on the same location, right? Agree? This is the second input to the first output. They are not on the same location. You want to be careful here. Let's look at this plot. Okay. Now plot here. From first input to the first output, they are on the same location at M1. All right. The transfer function from the second input to the first output, that they are not on the same location. Understand? I'm just talking about this, the phenomena here. So when you have those deep valley, all right, we call zero. It normally takes place at the same location for your input and output. So you have a sharp zero here. Now, if you don't, then you won't have the sharp zero like that. You do have this coming down and then going up. It's not so. So this kind of I call it, it's just two mountains together. You have a valley, deep valley, all right, like creek, all right, maybe like the canyon, very deep, coming down quickly and going up like that. But this is not. All right. So the differences between this blue line and green line is like that. The blue line is the same location of input and output. The G22, the same thing. All right, and then Z12 or Z21, they are the same thing. They will be like this, like that. Okay, now whatever you have here, if you can look at this phase angle changing, whenever you got a big, they change the phase 180 degree, and then they meet another phase, another the zeros, they also change too, and then the pole again they change. Now, what happens is zero? This zero means your nominator. Your nominator here. If you look at this nominator here, this is second order. This is only first order. And this is second order here. This is nominator here. If they are very small, if they have a root at zero, what does that mean? That means this one is very small. That's this one. Agree? If this guy here, if we have a root for this, that means this is going to be zero, right? Agree? The root of this polynomial, omega squared. If you solve that, it's complex number. If you solve that, and that root means this is equal to 0. At that root, that equal to 0. That means this is 0. G110. That means this. It won't be exact 0 because they are complex. And we gotta take the absolute value of the complex of that. That's from this point. Okay, so the 0 is from numerator, the pole from denominator, because if you have a pole root at here 0, means this is close to 0. Anything divided by very small value, that is a large value. Agree? So we have pole here, and 0, 0 here, and doesn't matter what the whole system, regardless from which input to which output, they all share the same denominator. They have to. But their denominator will be different. All right? Any questions? No? Yes.
Can you explain why this is 0 value here 1?
Is like this one?
Yeah, 0, why this polynomial is 0?
This one is 0?
Yeah.
If this corresponding frequencies, this is frequency, right? If this corresponding frequency and that frequencies make this term to be 0,
Yeah.
that means gain is 0.
Okay.
Gain is very small. It's minus 40.
Why not equal to 0?
It won't be 0 because there's no real omega. No real omega make this to be 0. You have a complex omega make this to be 0.
Oh.
Yeah, this has to be real.
This
This
is
is
real.
real. Right, so it can be very small only. Okay, it can be very small only because that's a complex. We don't have a complex omega. It has to be real omega. All right, so there's no such real omega make this term to be 0. No, the answer is no. But you can have the omega which is as close as possible to your root. The real omega as close as possible to your root. But that's a real one. It's not complex one. Understand now? The same thing, the pole is the same thing. Has to be real. But when you solve it, it's complex. But you have a real omega, which is the absolute value, which is very close to absolute value of your complex roots. Understand now? Okay, good. All right. Now, of course, if we don't have this, 0.00, if we don't 0.01, then what happens? You have a real omega that makes it to be 0, then this becomes infinite. That means what? There's no damping. This is the damping. If you don't have damping, you have a real omega. Then make the pole become infinite. Understand? That's true, right? That means when you oscillate to your system, then the amplitude could become infinite. In theory. I think in theory. I understand about that now? Whenever you have a damping, you don't have any real omega make this term to be 0. No. Okay? So that means you always got a damping. That's a damping from here. If this term is higher, this peak will be low. If this 0.01i is higher, then this peak will be low. Okay? That means your damping is higher, your peak will be smaller. Understand? Okay. So also good? Well, this is the curve. We use this kind of curve. We call response functions. to judge how good your control design is. Your closed loop. Whenever you plot the closed loop transfer functions, then compare with your open loop transfer functions, then you can see your controller has any improvement or not. If your controller make the peak down, your controller make the peak down means your controller is working. If the controller don't pull the peak down, that means your controller doesn't work at all. All right? This is why we talk about response functions, because that's the way that's the way we evaluate, we examine our controller design. Understand? Okay, so the frequency response function is important. That's why we do this. Any more questions? No? Yes? No? Okay. If now, then we move on. All right, and this is just give you some of the some concept about multiple degree freedoms. Multiple degree freedoms means if we have the mass matrix which is not 2 by 2, which is 10 by 10, 100 by 100, and 200 by 200 like that. The same thing. We have the damping matrix, and we have a stiffness matrix. We get all kind of the size for that. And of course, now when you design a real mechanical system or real civil engineering structures, then the degree of freedoms won't be only 2, won't be only 3. It could be 5, it could be 10, it could be 100. Then how can you do that, right? And this is just short. I'm not going to discuss very much about this, because that is something that I will discuss later. But here I give you some idea. But you gotta notice that I have a transformation here. The transformation is also an important concept for any control methods. In other words, most of the time we want to transform from our physical coordinates to some other coordinate. And we have many other coordinates we want to see. But one particular coordinate we call model coordinates that we use very often. What do we mean model coordinates? It's simply just transform from the physical coordinate to the eigenvalue space, so that we can see our eigenvalue there, we can see our mode shape there, something like that. And I will give you an example later to show you what I mean the model coordinate. So the model coordinate means just in the eigenvalue space, the coordinate in the eigenvalue space. All right, and so when we have a transformation, we transform the W to Q, for example, and then there's a phi, cap phi times Q equal by W, and this transformation is we assume this is physical coordinate. Assume W is the physical coordinate, and then Q is some other coordinate, and we have a matrix. This is called phi, and for example, I think most of you knows that Cartesian coordinates, right? Heard about Cartesian coordinate X, Y, Z, right? You heard about the, for example, polar coordinates. Yeah, so we transform from the, for example, from the Cartesian coordinate to polar coordinate. That means the transformations. That's kind of transformation we are talking about. And then for linear system, then we involve a square matrix called phi here. And we assume that the cap phi is invertible. That means the cap phi we can invert it to become cap phi minus 1 invert that W equal to Q, and we have instead of the W1, W2, W3, W2, Wn, then we have a small phi1, phi2, and to phi(n). In other words, we have 3 coordinates, which after transform, we have another 3 coordinates. It won't be like this. We have 3 coordinates here. After transform, we become only 2 coordinates. That's not what I'm talking about here. All right. So this coordinate, the number of coordinates doesn't before transformation and after transformation, they have to have the same number of coordinates. That's what I'm talking about here. Okay. Now if you transform the m w double dot, you sub your w double dot like this one, you w here, free q here, and then you put that w into your original equation, that's m w double dot, then you got this kind of function, you got this kind of transformation. So you have phi inverse m phi q double dot plus phi inverse E phi, and then Q dot plus phi inverse K phi Q, and equal to phi inverse B F U. But now, the important here is we have phi inverse M phi. Phi inverse M phi, what does that mean? A matrix is an inverse times a symmetric matrix, then times the matrix itself. There's a spatial characteristics for this kind of transformations. You know what? Example, after transformation, do you expect to change eigenvalue or not? No, that's right. If your transformation change your eigenvalue of a system, that transformation is not good. All right, so any transformation like this, phi inverse, assume phi inverse exists, times a matrix M times the phi, this kind of transformation we call similarity transformation. That means the eigenvalue won't be changed. Okay, understand? Oh, so similarity transformation is important. All right, so that means we write down here, this kind of transformation, what we call is the similarity transformation. So we have a phi inverse and phi, all right, that we call similarity transformation. And it does not change eigenvalue. Eigenvalue of M. All right. It does not change eigenvalue of M. Uh-oh.
Oh, the camera drops.
Sorry.
Okay.
Fix there. Okay. Fix there. All right. That we call similarity transformations. Okay. So the same thing. If you look at back, you can switch back now.
Okay.
Now the same thing. The similarity transformation for E, similarity transformation for K, they don't change. They don't change like this. They are not changing eigenvalue of this E. They are not changing eigenvalue of K. All right. So after transformation, we write the M becomes square M. This is like a Z become square C Q dot plus KQ equal to BFU. Okay. We say after transformation, we get that. Now, note that, now I write phi inverse become phi transpose. Did you see that? I say phi inverse in diagonal, I make them to be phi transpose. Be careful about that. Because N symmetrics, that E symmetrics, that K symmetrics. The symmetric matrix, the phi there, we call unitary transformation. In other words, phi transpose equal to phi inverse. All right? Any symmetric matrix, you can always find a unitary matrix such that that matrix, transform matrix phi equal to transpose equal to phi inverse. That's the property of symmetric matrix. All right? So if you look at carefully, that I explained a little bit here, and you cannot change phi inverse become phi transpose for any other non-symmetric matrix like this. No. This only exists for spatial matrix, such that symmetric matrix. All right. So now why would I want to do that? That's an important message here. What do we mean unitary? Unitary means any column of that phi matrix, any column, the length equal to 1. All right. Let me also explain a little bit here. You can switch back again.
Okay.
Yeah, I explain to you here. Phi. Now I have phi 1, phi 2 to phi n. All right. The length of phi I equal to 1. I from 1 to n. That means phi 1 transpose, this is a vector. This is a vector. Everyone has a vector. This is an n by 1 vector. This is an n by 1 vector. This is n by 1 vector. All right. Phi I transpose times phi j equal to 0 for I not equal to z. That means they are orthogonal. This orthogonal to that, that orthogonal to that. For the Cartesian coordinates, they are orthogonal, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Are they orthogonal? Yes. Same thing, like this. They are orthogonal. All right. Now, so when phi I t times phi equal to 1. It's not a good pen here. It's equal to 1. I think the whole way is going to work. Is that clear? I'm sure about that. Okay.
Yeah.
Maybe later on we find it better to depend on this. All right. Then, one more sentence. All the vectors are real. They are not complex. That's for symmetric matrix properties. Okay? So, that one, that was better. I plus all vectors, are real vectors. All right, this is only for symmetric matrix. The symmetric matrix have this kind of properties such that means 3 transpose 3 equal to an identity matrix. That means 1, 0, 0, 0, 1, 0, 0, dot, 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 0, 0, dot, 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 1, 0, dot, dot, dot. Okay, the identity matrix. That means 3 transpose equal to 3 inverse. All right. All this for any symmetric matrix, you can always find a transformation matrix that satisfies all the equality here, and they're all real. Any questions? By the way, I skipped the chapters of fundamental matrix. So whenever we need it, I just explain it here. All right? Okay. I let you have some time to copy it here, or later on you can view the video again from the YouTube. Okay. Now, any question about this? So that's for M. That's the same thing for data. Okay. 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 I think you will have enough time to copy it, right? Then let's switch back to my note again. This is a very interesting things going on here. I need to explain to you. So this is why I spend a little bit of time here. Okay. Now we call this square M equal to the phi transpose M phi. We call this C becomes a square C is a phi transpose E phi. We call this square K equal to phi transpose K phi. All right. Now let us look at some property here. Assume we can find a phi such that transpose M times phi equal to I, equal to a identity matrix. All right. That's very interesting, right? Yeah. I'm talking about the transfer function. Is there any matrix phi such that phi transpose M phi equal to identity, and then phi transpose K phi equal to my frequencies diagonal there? Well, there's a theory that can be proved. That matrix always exists if M is positive definite and K is semi positive definite. That means my omega, some of my omega, my frequencies can be 0. Okay. And to prove that is not very difficult to do that. Matter of fact. So, but I'm not going to prove it for you here. It will take a little bit time for that. But we assume that we can do that. So, assume that we can find a phi matrix such that phi transpose m phi equal to I and phi transpose k phi equal to my cap omega square. That cap omega square, it will be my diagonal omega 1, omega 2, and omega n. All right. Okay, for time being, we just forget about C because that we cannot simultaneously diagonal K and C, and there are no such things. Only when we have a spatial matrix called C equal to alpha I plus beta omega square. Now, let me you have some students from mechanical engineering, some students from civil engineering, right? Right? Have you heard about damping ratio? I told you, well, I taught already damping ratio, right? Now, we always assume the damping ratio are the same ratio for all the frequencies. Is that right? Just we hear about something. Some people, some engineering, they always say, okay, I have a damping ratio is 0.01, at 1% damping for all my frequencies. But you might hear something like that from your colleagues or from your when you go out to some industry, work there, and some of the engineers will say, oh yeah, we can assume like that. As a matter of fact, the damping matrix is the matrix. There's no solid theory to derive that matrix. So most of the cases, the engineer they will assume, say, oh, we have a damping ratio that's 1% for all the modes. Okay, that is not bad, honestly. That's not a bad assumption. In many cases, that assumption is good enough for us to do a real to solve a real problem. Okay. All right, and so this is these equations. In matter of fact, that give you the we call proportional damping ratio. There's a proportional damping. In other words, we assume all the frequencies they possess the same damping ratio. That's what it happened here. So we have beta here, we have a beta here. That means omega squared is this diagonal matrix. That beta is a constant. That means I have constant multiplied by all the frequencies down there. It's a damping ratios. Assume I have the same constant, the same damping ratio for all the frequencies. That it means. Agree? Now, if we have this kind of assumption, then we can simultaneously identify the M matrix and the E matrix and the K matrix. Okay? Only under this case we can diagonalize all the matrix by a matrix called phi. All right. So let me just summarize it a little bit here, and then you will understand what I'm talking about now. Okay. Now this is this one. Yes. This one. Okay. Now this is my system M, right? And I have zeta and then I have K in physical coordinate. Okay. Now, giving a transformation matrix, P. All right. Then that transformation matrix, we happen to transform M, become like that. So this is my square M. And then we transform zeta, become C, square C, equal to phi transpose. And then the phi. Then we transform square K equal to, all right. After transformation matrix, this become identity matrix. This is a diagonal matrix. And this, another diagonal matrix. And this diagonal matrix will include all my frequency in there. Okay? And I already show you this only occur that there is a C, that C there equal to alpha 1. So this diagonal matrix will be alpha times I plus beta times omega square, and this is my omega square, the cap omega square. Only that is satisfied. However, in practice, there is no such matrix will satisfy like that. No, but this matrix, this Z matrix, there's no any clear or any solid theory allowing us to derive or develop this damping matrix. Okay? Because we really don't know very detail about the damping mechanism. That's true. So in many cases, in the system, mechanical system or civil engineering system, many cases in this matrix here, we really make some assumption this is true. That just try to simplify the problem so that we can design controller or we can design something else for the system under considerations. Any questions?
So how would you select these constants, alpha and beta?
Oh, good questions. This beta, this normally we let this to be 0. All right. Normally we say this beta to be, if 1%, that means 0.01, for example. Like that. That's and in by experience, that 1% or 0.5% damping, that's what we observe from a real, laboratory testing and so on like that.
So definitely, okay, I'm saying no. That alpha is constant for the mass matrix. I don't know if I'm
Right.
right.
In other words, that means this is proportional to the mass matrix plus proportional to the K matrix. That's what it means. That means this is proportional to something like M, and proportional to something like K. In many cases, we don't worry about M, we worry about the K. So this is what we have. You remember that I talk about 2 theta omega, and then W dot, do that one, then plus omega square W plus M plus the W double dot. Remember these equations?
Okay.
Yeah.
Square.
This is the damping ratio we're talking about. It's not exactly the same like this one, but this is related to that damping ratio. Okay. Yeah. So that's what we mean. Okay. But anyway, this is all the theory, and why we want to do this. I explained to you that we like to simplify our mathematical model for our physical system. That's the purpose. So many cases, if you derive very complicated nonlinear dynamics equations, it's not solvable anyway. So why you want it to be so complicated? We have to simplify some way. Okay, that's the purpose. So this is the way we simplify it. So I already talk about this data matrix or this C matrix, this data matrix, this damping matrix. There's no really a good like a Newton law. Say, okay, now this is it. This is my damping matrix. You can base on that law and to get my damping matrix very accurately. Right? And that's true. Particularly in the space application, that's true too. Okay, that's switch back to my notes. Okay, and that I think that finish these slides, and I will give you example in the next slide, and then you will see what's going on. So critical freedom like this. And this example will give you a very nice example, and you can see what's going on. So I have a transformation, for example, like here, and then I have an M happen to be only 1001. You see that? I happen to be say 1001, right? And then zeta equals 0.02 minus 0.01, 0.01, 0.02. And then I have a 2 minus 1, 2. That's my K. And that's corresponding to this figure there. And you have M1 equal to M2 equal to 1 equal to Z1 equal to Z2 equal to Z3 equal to 0.01. And K1, K2, K3 equal to 1. If you look at that, and then if I have a transformation like this, and I can transform that matrix. If you look at this carefully, phi transpose M phi, they originally 1001. I did not change their structure at all. There's such phi like this, and they are orthogonal. If this matrix is transposed times this this vector, column vectors transposed times this column vector equal to 0. Agree? And I have a square root over here. That because I want a length. This 1 square plus 1 square divided by square root of 2 equals 1. So I want to normalize it so that they are unit vectors. Because you need a unit vector such that phi transpose becomes phi inverse. All right? If you don't normalize it, that's not true. You can do that. Okay? And then if I transform, if you look at this, I use this matrix, transform that, the E matrix, I become diagonal again. This is diagonal. See, this is not diagonal. It's diagonal. 0.01, 0.03. And I use the same matrix, transform this K is here, and this becomes diagonal too. 1, 0, 0, 3. As a matter of fact, square root of 3, square root of 1, that's my frequencies. That's omega squared. But they're supposed to be your natural frequencies. It's not damped frequencies. So you have to be careful about that. So after transformation, then I can find, this matrix I can find, instead of the couple, this 2 degree freedom, the physical coordinate, they couple together. This is coupled together, Then, if it become all diagonal, they are not coupled anymore. See, this diagonal, this diagonal, this diagonal, Q1, Q2, they are not coupled. Q1 and Q2 are not coupled at all. So you can see the advantages here. You can solve the Q1 and Q2 independently. Right? Does you think it's easier? Rather than you solve the matrix equation like this. Instead of solving the matrix equation 2 by 2, I solve 2 independent second order differential equations. You think that's better? Huh? I think that's better. Yeah. Also, you can see better because you can see your frequencies here. Everyone, your frequency is square root of 1 is 1. Your frequency is square root of 3, right? Your system frequencies is there. Your system damping is there too. That's my system damping there. This is my eigenvalue damping here. This. So if you transform to this Q coordinate, we call model coordinates, means they all decouple. Okay? Is that understandable now? Why model coordinate? Model coordinate means we can see the frequencies, we can see the dampings, we can see the motion later on. I show you how to do it. Any questions? I think we better take 10 minutes off, right? So you have time to digest. Okay.